Welcome to this unit on audio data compression. We are going to begin by talking about general techniques for compression, and then we will see how these apply to audio data compression. First of all, the word compression just means representing data with fewer bits. And it is generally accepted that there are three techniques, general techniques for compression. In common models of compression, we think of data as consisting of a sequence of chunks or symbols, and the first technique addresses each symbol independently and says that we can reduce the redundancy in our representation for each symbol. So, for example, Unicode defines over 65,000 characters, and in some representations of Unicode, 32 bits are used for every symbol. But as you may know, there are 8-bit encodings, specifically UTF-8, where at least some documents, like ASCII documents, can be represented with only 8 bits per symbol, eliminating a lot of redundancy. Coding redundancy also applies to quantization in audio. There are also variable length codings used to exploit or to reduce coding redundancy. The second general technique is reducing intersample redundancy or intersymbol redundancy. For example, if I were to say, hey, I've got this text and it says WW something, can't read this third letter. You would probably say, well, it's probably W as in World Wide Web. What else could it be? And so that's an instance where this third W is highly redundant. It's really implied by the first two Ws. And if we can exploit that kind of inter-symbol redundancy, then we can do better data compression. We see intersample redundancy in image compression. So, for example, faxes don't send every black and white pixel. They send the length of the runs of white pixels because it's known that once you have a white pixel, it's very likely to be followed by a white pixel. Similarly, we could take advantage of silence in audio, low amplitude over most of a frequency domain representation. Object descriptions, for example, let's look up here. The very first letter in the slide is a G. In the video, this is actually just a bunch of pixels, but in PowerPoint or PostScript representations, this G is, all of these G pixels are generated from one object, the letter G. And so by encoding the object rather than the pixels that render that object, we can exploit a lot of redundancy in those pixels. And the third compression technique is psychoperceptual redundancy. So in audio, this has to do with masking effects, noise and distortion thresholds. Basically, the idea of psychoperceptual redundancy is that it's not the information that's important, it's the perceptible information that's important. So if you can't hear it or you can't see it, then we don't really need to put it in the data. Of course, that's not always true, but that is the basis for psychoperceptual redundancy. So all three of these techniques are very important. They are found in all fields: image representation, databases, even the design of Unicode representation considers some of these compression techniques. Also, zip files use some very interesting intersample redundancy elimination techniques, and so on. Let's talk about ways of using coding redundancy to compress audio. We'll start with PCM, or pulse code modulation, which is a linear encoding of sampled audio. That is considered uncompressed audio that we want to compress. One way to compress PCM is to use a representation called mu law. That's mu as in the Greek mu, not u as in the letter U. Mu law is usually described as a logarithmic encoding of data, and it's actually a floating point recording. So the exponent is logarithmic, but there's a linear mantissa. Anyway, this is an 8-bit representation that represents a 13-bit dynamic range. Similarly, there's a slightly different standard called A-law, which encodes a 12-bit dynamic range. And here we can see the PCM encoding represented by the left-hand side of the scale, and a quasi-logarithmic mu-law-like encoding on the right-hand scale. And so what you see is in PCM, each quantization level is separated by an equal amount. So this might be, this would be represented by 0, this is 1, 2, 3, 4, and so on. So linear doesn't do a really good job of encoding low amplitude portions of the signal, or looked at another way, it spends a lot of bits on the higher amplitudes of a signal. On the other hand, mu-law has very closely spaced quantization levels near 0. So it's very good at encoding low amplitude signals, and the spacing increases as you go to higher amplitudes. So it introduces more noise or more quantization error at high amplitudes. But of course there's more signal, so it's, in some sense, it's a constant signal-to-noise ratio independent of the amplitude of the signal. The simplest way to implement mu-law is to use lookup tables. So if you're going from 16-bit PCM to 8-bit mu-law, you just need a table for all possible 16-bit values, so that's about 65 kilobytes, and you store into each entry in the table the corresponding mu-law value. And similarly, if you want to go mu-law to 16 bits, you only have 8 mu-law values, so that's a table of size 256 containing the 16-bit versions of each of those quantization levels. Mu-law is common in telephony, where audio is fairly low quality, 8-bit. And what about using more bits? Use the mu-law technique, not for low quality telephones, but for high quality music. Well, it's been tried, of course, and studies show that 16-bit PCM is better. If you're going to use 16 bits, it's better to use PCM. And I think that's because 16-bit gives you such small quantization levels, even close to 0, that a non-uniform distribution of quantization levels doesn't really help. And if you can't afford 16-bit PCM, then there are other techniques we'll look at, especially perceptual coding techniques, that are just much better than mu-law, although much more expensive computationally. Now let's look at the enter-sample redundancy approach to compression. This one says that previous samples should be somehow predictors of successive samples, and there's redundancy there that can be exploited. So the simplest way to approach that is delta PCM. We just encode the differences between samples rather than the samples themselves. This gives you about a 6 dB or 1 bit improvement over PCM for speech. So it's a reasonable thing to do at lower qualities. Actually, it's not such a good thing for music audio, but let's continue looking at other things that can be done. The next thing that we can do is adaptive delta PCM. So in this case, rather than encoding the differences, we're going to encode the differences, but we're going to adapt the scale factor on that encoding according to whether the signal is moving slowly or rapidly. And this helps even more. It gives you about a 10 to 11 dB in signal to noise ratio improvement over PCM for speech. So here's what delta PCM looks like. And here we're just using 1-bit encoding. And so we'll encode a positive step as 1 and a negative step as 0. And we want to encode this signal here. And so we encode a sequence of 1s, trying to track the signal as best we can. And finally, we catch up to the signal, and the signal is coming down, so we encode some 0s. And notice that when the signal is steady, we have to encode that as alternating between the two. We have a fixed step size. And here's a flowchart for how we do this encoding. We take the output and integrate it to reconstruct the signal, and we compare this reconstructed signal to the incoming signal, and whenever we are too low, we output a 1. Whenever we're too high, we output a 0. So that's what the quantization step does, is it just decides which direction we should go to more faithfully encode the input. Here is the 80 PCM example. We have the same signal that we're trying to encode. We are initially below the signal because the signal is increasing, so we output a 1. And when we output the second one, we double the step size. And when we output the third one, we double the step size again. So if we are outputting a sequence of 1s, then, or for that matter, a sequence of 0s, the step size will increase. When we change directions, then the step size decreases. So here we output a 0, we get a small step down. And what happens when we hit the end of the signal where the signal is steady, we are alternating. Here's 1, 0, well, 0, 1, 0. We are alternating, and that reduces the step size. So we're better able to encode slowly varying signals. And because the step size can increase, we're also able to better encode rapidly changing signals. We enforce a minimum step size because otherwise, if the signal was constant 0 for a long period of time, the step size would just become exponentially small, and we'd be very slow in responding to a change in the signal. Here's what an 80 PCM coder looks like. You'll notice the bottom half is just like a DPCM coder. We integrate to reconstruct the signal, we compare, and we quantize, deciding what to output. And the only difference is that in 80 PCM, we have some step size logic that is derived from the output and fed back into the quantizer, so that we, and the integrator for that matter, so that we know what the current step size should be. Now we can continue along this line. Delta PCM works by taking differences between samples. Adaptive delta PCM looks at not only the difference between samples, but our history in constructing the step size. Maybe we could look back further and say that the next sample can be predicted by some number of previous samples. There's some kind of correlation going on there. So DPCM is a first order predictor, and we can have nth order predictors that form weighted sums of the past n samples. And like ADPCM, we need to adapt those weights to the signal. So as we're listening to the signal, if there's redundancy, we can actually kind of learn on the fly what the best weights are and apply those to predict the next sample. You can get a gain of about 3 or 4 dB, so not a huge amount, and there's very little gain to be had beyond 4th or 5th order adaptive prediction. You might wonder, why don't we use delta PCM instead of regular PCM for music? And the answer is that the delta can be really big. If we have a 16-bit range of PCM samples, then the delta is twice that. The delta could be positive from lowest sample to highest, or negative from highest to lowest. So it actually takes 17 bits to encode delta PCM equivalent without loss. And so if we go to delta PCM, we're losing a bit, or we're losing 6 dB, and so delta PCM sort of has to be 6 dB better than PCM, and that just doesn't happen. Experiments have shown that PCM is better. Let's briefly review. We talked about uncompressed audio, which is PCM, or linear independent integer samples. We talked about different forms of data compression. The first was coding redundancy. And for example, mu-law and A-law are different, more compact representations of PCM samples. We talked about inter-sample redundancy, delta PCM and adaptive delta PCM, which try to exploit the fact that signals are generally continuous and have small changes from sample to sample. And finally, we mentioned psychoperceptual redundancy as a third area. And in the next lecture, we'll look at MP3 encoding and how psychoperceptual redundancy plays a big role.